Welcome friends to a session of finite element methods for fluid dynamics. I will be telling you about this course in this session. So that is the number for the course 618, and I am Sanjay Mittal. My office is in the low speed aerodynamics lab in the Department of Aerospace Engineering. My phone number is listed over here, so that is one way you can contact me. But the best way to contact me is through my email address. So you can write an email to me and we can schedule either a Zoom meeting or we can talk over the phone. So just to let you know what this course is about, it is essentially introduction to the finite element method and how it can be applied to fluid mechanics. Okay. So as you are aware that most phenomena in engineering, including fluid mechanics, can be modeled by partial differential equations. So in this course we are going to be looking at ways of modeling those phenomena as well as how to solve those partial differential equations to be able to understand them. Now obviously when you are interested in a numerical solution, some kind of an approximation will be involved. Okay. So there will be an error between what the exact solution is and what you would predict numerically. So most numerical methods would talk about error control, and in fact the philosophy of how the error is to be controlled is what distinguishes one numerical method from the other. So there are a host of numerical methods and a finite element is just one of them. Okay. So the objective of the course then is to provide you an exposure to the finite element method. It is one of the many methods to solve partial differential equations. And I hope that by the end of this course you would be able to figure out how to design a method to solve a problem of fluid flow, and then you should also be able to appreciate any other method if you would like to develop it or use it in future for solving fluid flows, or for that matter any other phenomena in engineering. Okay, so about the logistics of this course, as you must be aware from the schedule, we have been assigned 2 teaching hours. These are on Tuesdays and Thursdays, starting from 5:15 p.m. Till about 6:30 p.m. So there are only 2 hours every week, and I would like to pre-record all the lectures and put them online through one of the portals, and you can access them. And then to have more discussion on these material, we can actually use these hours, either one of them or both of them every week, to hold a discussion hour, or for that matter if I would like to have certain evaluations like maybe short quizzes or maybe to discuss the term papers. This is an hour that is available to us and we can use this. If you have any doubt about the material which is going to be available online, you can, of course, you are most welcome to discuss them in the discussion hours, but you can also contact me by the phone number that was in the previous sheet, or you can write an email to me and we can have a discussion on email or in person. Okay, a little bit about the course content. So as I spoke to you just a while ago, the fact that we are interested in a numerical solution already implies that we are okay with incurring some error, but we need to have a bound on the error. So suppose I want to predict on the trajectory of, let us say, an airplane, okay, and it is going to be affected by the airflow, and I want to predict where the airplane is going to land, let us say in a cross flow environment. So there is an error that I have, a tolerance that I have for the error, and I should know that what does my method do or how tight are these bounds. Okay. So, what we are going to look at first is we are going to take a small toy problem. In fact, it will not be a partial differential equation, it will be a very simple ordinary differential equation. And then we are going to talk about the error of the numerical solution versus the exact solution, and then we will try to see how we can control this error, okay, how we can set up a formulation whereby we can talk about where the error is and how to minimize the error and so on. In fact, that is what will set us in a framework where we can distinguish between different kinds of methods. So, you must have heard of these methods like the finite difference method, the finite volume method, the finite element method. So, if we had to argue that how are these various methods connected, this actually would be the framework where we would see how one method differs from the other. Next, what we will do is we will take some very simple finite difference method, very classical methods, and I will try to convey to you what is numerics all about. Okay. So, when you discretize a problem numerically, how does the error change when you increase your resources, okay, and so on and so forth. What happens in one dimension, how do you generalize things to multi dimensions like 2 and 3 dimensions. So, some very simple ideas just to get us started, both in terms of writing simple programs as well as getting familiar with the terminology. Then we move on to the topic number 2, where we will take a simple one dimensional boundary value problem and talk about the solution of this problem, which is the exact solution, and then we will also formulate it in an integral form, which is called as the weak form, and then we will see what happens to the boundary conditions. Okay. So, some of these boundary conditions would be the Dirichlet type conditions, some would be the Neumann conditions. So, what happens to them, that is what we will look at in the first part of this module. We will also show that you can actually take a problem in the strong form, which is essentially the differential form of the problem, and show that it is equivalent to the weak form. We can also show that the weak form is the same as the strong form. So, they are actually synonymous, and depending on what method you want to use, you could either start from the strong form of the problem or the weak form of the problem. And then we will come to the basics of the finite element method, the foundation, which is actually the Galerkin's approximation. So, this is the first time that we will actually talk about the finite element approximation of a simple one dimensional problem. Okay. And we will see that, as in other numerical methods, most of the time is actually consumed by the solution of a linear equation system. So, the beauty is we start with a simple ordinary differential equation, and by using the Galerkin's approximation, we will reduce the problem to something like Ax equal to b, okay, just a simple system of algebraic linear equations. Then we will study a little bit about the kind of approximation it is. So, we are going to use linear finite element space. We will talk about this in more detail as we move along, and then we will talk about some ideas of how to put it in a framework where things are more efficient. So, it is one aspect of a numerical method to design an algorithm, and it is yet another aspect how to do it efficiently. Okay. So, in this course we are going to look at not just the algorithms, but also the framework in which these can be implemented in an efficient way. So, I will show you some ideas about what is meant by an element point of view. So, the name finite element roughly implies that you are going to take a domain. Let us say your domain is a 3-dimensional domain, maybe it could be the room in which you are sitting, and you are interested in looking at the analysis of the flow of air in this room. So, you would discretize this room into elements, okay, many elements. So, that is the element we are talking about. So, we will look at the element point of view and how do you assemble information from all the elements to get various equations, which in fact you are going to eventually solve to get your final answer. Okay. So, there is an element point of view and there is an equation point of view, and we learn how to move back and forth between them. So, this would be done in one dimension, okay, just with a toy problem to give you a flavor of the most basic finite element approach, and as I said, the foundation is the Galerkin's approximation. Next, we are going to worry about, can we generalize this in 2 and 3 dimensions. So, that is the module number 3. So, we will complicate the problem a little bit more in the sense that now we will go to first 2 dimensions. So, now we are necessarily going to deal with a partial differential equation. So, suppose you look at the heat conduction equation. In 1 dimension it would be just heat conduction in a bar, whereas in 2 dimensions it would be heat conduction on a plate, and maybe in 3 dimensions it would be heat conduction inside a solid object, and so on. So, we will take an example from the heat conduction problem. We will also generalize it to essentially linear elasticity and also some aspects of fluid dynamics. Okay. So, we will look at compared to 1 dimension, what are the complications in terms of the equations themselves as well as the boundary conditions. In fact, what we will see is that even approximating the boundary is going to be a challenge in multi dimensions. So, just to make you appreciate, if you think of a problem in 1 dimension, then the boundaries are actually 2 points on either end of that domain. But when you go to 2 dimensions, for example a plate, then your boundary is a closed curve. It could be a circle, it could be a rectangle, so it may have corners. Okay. And then when you go to 3 dimensions, then your boundary is actually a surface. Okay. So, there are problems even in approximating a boundary. Just to give you an idea, if I had to model, let us say, flow around an airplane, then even to model the surface of an airplane is a big challenge, okay, because a surface of an airplane could be extremely complex, and to be able to put grid points on the surface and then join them via some elements is not so trivial. In fact, the modeled surface that you may get could be a little bit different than the actual surface of an airplane. In fact, even a sphere. So, if I had to model a sphere using finite elements, and let us say I want to use some kind of linear elements, I would realize that I have approximated the surface of a sphere with a multifaceted polyhedra. So, it is not a smooth surface anymore, it consists of some panels, okay. And so there are issues in applying boundary conditions and so on. So, we will refer to those issues in module number 3. Next we go to the module number 4, where actually we are going to talk about the generalization of what we learn up to module number 3. So, we are going to talk about a family of elements called the isoparametric elements, which essentially means that the way you approximate the geometry and the way you approximate the solution itself is of the same order. Okay. So, you use very similar ways to not just approximate the geometry, but also your solution. Think of the following. Suppose I am interested in looking at flow past a sphere, and to represent the sphere I could say, well, the surface will be represented by higher dimensional panels, not just linear panels, not just straight panels. Okay. But the flow I would like to represent with linear elements. So, I could have higher order elements for the surface and a little bit lower order for representing my solution. So, that is not isoparametric. Isoparametric would be if I use linear for the geometry, then I use linear for my solution space. If I use quadratic for the geometry, I use quadratic for my solution space. So, isoparametric obviously is a little bit simpler than either subparametric or superparametric, and then we are going to look at some programming concepts, okay, how to implement them in an efficient manner. This will bring us to the idea of, in 2 and 3 dimensions, generalization of linear elements. So, linear in 1 dimension would become bilinear in 2 dimensions, and it would become trilinear in 3 dimensions. And suppose I want to go to even higher order approximations, we will look at that aspect also. Having done that, because we are in the framework of a weak form, which is, as I said, an integral form of the differential equation, we will soon realize that exact integration is not possible. So, we will have to go to numerical integration. So, there are some rules that you are familiar with, like the trapezoidal rule, the Simpson's rule, and so on. And we will realize that maybe they are not the best. Okay? So, the optimal rules are actually a little bit different. So, we will introduce the concept of numerical integration. Gauss quadrature is one method, which is, I will show you, it is very efficient. And then we will move on to the concept of what is called a shape function, the finite element functions, and how to compute their derivatives. So far, if you go up to module 4, you should be able to look at a linear partial differential equation, but steady. Okay. For example, steady heat conduction in 2 and 3 dimensions, you should be able to solve that problem by the end of module 4. Next comes the idea of what happens if you have unsteadiness. Okay. So, you have time dependence. So, it turns out time is a little bit different than space, and you can guess why. In space, I can move in either directions. So, if I have a positive x axis, I can go in positive x, I can go in negative x, there is no problem. But time does not allow me to do that. I cannot go back in time, I have to respect causality. Okay. I cannot go back and fix things, time always moves forward. So, the numerical treatment also is a little bit different. You cannot do the same treatment for space and time. So, in module number 5, we are going to learn about how to handle time discretization. Okay. So, we will take the same problem as we had taken earlier, the toy problem, let us say in 1 dimension, but now we will add an unsteady term to it, the time evolution term. And we will see if we now apply the Galerkin's method, including that to the time dependent term, then how can we approximate it. Okay. So, we will look at one method. There are of course many methods to look at the time dependence, but I will show you one, which is the generalized trapezoidal method. It is a family of methods, and it has some free parameters like a quantity called alpha, and we will see that for different values of alpha, the method, the trapezoidal method, could give you different levels of accuracy, but it also has implications on the stability of the method, okay, stability of the error. So, we will use that module also to understand what is meant by the stability of an algorithm, what is meant by the accuracy of an algorithm, and in fact what is meant by the convergence of an algorithm. So, as you will appreciate, what I really want is from my numerical method, that if I solve a problem using, let us say, some resources, computational resources, and I now double the number of resources. So, suppose I was using 100 hours of computer time to solve a massive problem, and now I say I would like to use 200 hours of computer time. Earlier I was using some approximation which used, let us say, 10 GB of RAM, and now I am allowed to use, let us say, 32 GB of RAM. Then obviously as I use more resources, I must get a better solution. If I come up with a numerical method where my error seems to blow, it seems to increase as I use more computer resources, obviously that is a bad method. Okay? So we will look at issues like convergence, accuracy and so on, both in space and in time. And I will show you that not all algorithms have desirable properties. So we must use only those algorithms which have these at least basic desirable properties of convergence, consistency, accuracy and so on. So we would have then done a linear problem, both steady and unsteady. And before we go to incompressible flows, the fluid flow equations, there is one topic that we would like to introduce, and that is how to deal with nonlinearities. So I will give you a few lectures on how to deal with nonlinear problems. So you are already familiar with a method like Newton-Raphson, okay, maybe the secants method. So we will briefly go through those and look at what are the limitations of those methods, when do they work, when do they not work, and then we will be ready to go to incompressible flows. Now these are extremely complex problems. So if I compare a flow problem, let us say with incompressible equations, to a heat conduction problem, then the challenges are quite complex. So as you are aware, the continuity equation makes a big challenge. Okay? As you are aware that in the incompressible flows, the pressure term is one order lower than the viscous term, which actually is driven by the velocity. So these kind of incompatibility between the order of the various transport terms in the equations, they also have implications in what is the order of representation that I can use numerically. Okay, in the sense that if I am using, let us say, second order terms for velocity, and I try to use a second order term for pressure or a second order approximation for pressure, you can see there could be in principle some problems because the order of derivative is different for the two. So then how do we deal with that? Okay. Also what happens that when you have a convection term, it kind of changes the nature of the transport. So the diffusion term, which is actually the second order term, is more like an elliptic operator, whereas when you include the convection term, then you would not remain elliptic anymore. And how to deal with those, we will actually look at these items in this module. Having done that, we will move over to some very preliminary issues with compressible flows. Okay. So compressible flows have their own challenges, for example shocks. Okay. So how do you deal with representing shocks? So we are, most of the time we would be using continuous functions, but then at least in a inviscid framework, shocks lead to discontinuous solutions. So how do you represent discontinuous solutions using continuous variables, and what kind of problems it poses? How do you capture shocks? So those are some of the challenges we will try to address in this part of the course. Of course, it will be rather brief. What we will realize is that the traditional Galerkin method, which works very nicely for heat conduction problems, is not going to work for flow problems, both for incompressible and compressible flows. So we will have to deal with some new kinds of framework which are called the Petrov-Galerkin methods. Okay, so we'll look at them. I don't want to harp on it right now, but when the time comes, then we'll see that these are very clever modifications to the Galerkin method to make them work. Okay. So, those of you who are familiar with upwinding in finite difference methods, you will realize that if you use a staggered grid for solving your equations, that works better than grids where the pressure and velocity are not staggered. So, these kind of methods actually allow us to do similar things in the framework of finite elements. I am also going to expose you to certain special topics, time permitting. For example, how do you implement these in the framework of high performance computing? So if you use your standard algorithms on sequential computers versus if you had to implement these methods on parallel computers or parallel vector computers for large scale computing, then what is it that you should keep in mind? What are the issues that come up when you do mesh generation or grid generation? And a little bit exposure to graphics and visualization. Essentially, what are the tools that one needs to practice good CFD to be able to come up with meaningful solution? Many of these special topics I am hoping would be covered actually by you through your term papers. So, the idea is that some of you will get together in a group, study maybe one aspect of a topic and then present it to the rest of the class, and thereby all of us would learn something new more than what is in the lecture material. So, that I think would be a good way to look at special topics. I of course will assist you in choosing the material to make these presentations in the special topics. Okay, a little bit about the recommended textbooks or the reference books that we will follow in this course. So, the first few lectures where I talk about the finite difference methods, very simple finite difference methods, that could be found in several books, for example by Professor Krasik. This is a very classical book, Advanced Engineering Math. Many of you must have glanced through it or followed it in your first courses in math. So, it has a very good chapter on numerical math, and I am going to use this to motivate some very simple topics in finite differences. The bulk of the course would actually be from this book. So, we will be following the second book here listed in this list as almost like a textbook. So, Professor Hughes has been a father figure in introducing finite element analysis in fluid flows, and this book is very well written. It starts from the very basics and builds up the method. So, you can in one single book you can find the finite element method itself in space, and then how do you do discretization in time, ideas of stability, convergence, and how to choose elements, approximations for fluid mechanics. So, this book has several versions, but the latest one is from the Dover publications. So, you should be able to find a copy of this. I strongly encourage you to get a copy of this book, and it would help you even later when you want to use the method. The third book is by Professor Fletcher with a very general title, Computational Fluid Dynamics. Again, it is a good reference book. Similarly, number 4 is a book by Professor Charles Hirsch, which builds up more on finite difference, finite volume kind of methods, both for internal and external flows. We will use this as a reference book. In fact, it is a little bit easy reading compared to the book by Professor Hughes. So, maybe if some of you find this going a little bit tough, you can first maybe read a little bit from Professor Hirsch's book and then go back to the book by Professor Hughes. This book over here is again fairly easy to read by Ferziger and Parik. computational methods for fluid dynamics, very easy reading, and in fact I like this book because it gives you a very nice overview of the various methods, but I would suggest this is more like a reference book, and it would give you a very nice overview of the various methods. This book number 6 is a classic again. In fact, when I was an undergraduate student and I took my first course in CFD, then in fact I was taught from this book, okay, by Professor Anderson. So this is more on finite difference methods, and it again builds the topic very in a very nice manner, starting from the basics, again very easy to read. So some of you may want to look at this book as well. This is a more recent book, okay, I mean recent in the sense almost a decade old, and I like this book very much. So this is, as you can see, the title itself says finite element method for flow problems, and Professor Donia and Huerta, they again start from the very basics and build up a finite element method and all its nuances to address fluid flow. In fact, we will use this book towards the topic where we move to fluid flow problems. So one of the treatments that I really enjoy in this book is how they look at convection driven problems and how to design a upwinding method for a convection problem. So we'll specially use this book for that part of the course. In addition to this book, there are many other books available over the internet in our central library, or you may have personal copies. This Professor Zinkiewicz, Professor Reddy, Professor Gresho has an extremely good book on incompressible flows. Professor Klaas Johnson has a nice book on finite element analysis. And in addition, once in a while I will refer to journal articles, and if you come across any and you would like to point them to the class, you are free to do that. So we'll have these various forums on the portal, which I will inform you as we move along in the course. So that's about it for the reference material and the textbook in this course. I wanted to say a few things about the grades and the policies in this course. I am very aware that this is an elective course. So this is not a course which you are supposed to take as a mandatory course, or you were forced to take it. So I am very aware that you took it because you actually you have some interest in the course, and it's purely for learning. But nevertheless, there will be some policies for evaluating you and giving you a grade at the end. So just to lay out things a little bit more explicitly, I thought I will highlight the policies. So I encourage you to go through these lectures. I know online teaching can be a little bit tricky, and you may not find the lectures as interesting as you would have otherwise found when we could meet face to face. My apologies for that, but I hope we can make up for that by you contacted me for discussions, either when we have live discussion hours, or feel free to contact me otherwise either through email or phone, and we'll try to do the best we can. We can also use the forum for discussions, so that others who may have similar questions but did not have the courage to ask can also go through that material. Okay. So I strongly encourage that you attend the online discussions and the sessions in addition to the lectures. This is primarily because sometimes in this kind of a course people would come up with some issues that not all of us may have thought through earlier, and they could benefit us. and also in these sessions I may make some announcements, and I would expect that you would be responsible for any announcement that I make. Okay, there will be a series of home assignments, and they will be in modules so that they contribute to a final project. So, just to give you an example, suppose the target was to be able to make you feel that you can solve flow past a body by the end of the course. So, that would require, for example, a grid generation. Then that would require you the ability to show that you can solve Ax equal to b, a system of algebraic equations, that you can carry out numerical integration. You can come up with a module to write finite element functions and their derivatives. So, the plan is that I would work them out as assignments, and then later you can just use these modules which you would have from earlier assignments and make them into a final project. Okay. So, therefore, my suggestion is that when I give you a homework assignment, please try to do it in a manner that it is modular, okay, that you should be able. So, suppose I ask you to solve to demonstrate that you can solve Ax equal to b. The idea is that you should be able to use this later when you do your project, and you can call that as a subroutine. Similarly, if you do numerical integration, then you should be able to call that module and give it any function that you would like, and this subroutine should be able to integrate that. Okay. I get this question quite often in the earlier versions of the course that I have taught, that what is the programming language that I recommend. So, I will give you the answer that I usually give, that I have no recommendations or preferences. You please use whichever programming language you are comfortable with. Those of you who use Fortran, we are okay with that. If you want to use C, or if you want to use C++ or Java, anything that you desire is okay. I mean, this is a course on the finite element method and not as such on a programming language. So, I am not going to be able to test you on a programming language. That's not the intent of this course. But those of you who are scared of programming, you have two options. A, you please get used to programming. In fact, you can use MATLAB. MATLAB is hardly any programming, it is simply just writing some scripts. Or if you really feel scared, then you might have to drop this course. Okay. You know, practicing numerics is more like practicing cooking. You cannot say you are a good cook, but you only know the recipes. Okay. You cannot indulge in cooking. So in a course which pushes numerical methods, I think it is only fair that you implement those methods, and that would certainly involve some programming. Okay. You can even use different languages as you move along if you are comfortable with that. So, you could, for example, do some modules in Fortran, some others in C, and then of course these languages allow calling subroutines in different languages and integrating them. I am not saying you should, but should you feel the need to do that, I think that is perfectly acceptable. Point number 4, I already alluded to this. This is actually a way that I have been enjoying teaching this course. So, you know, there are two aspects of the way you can learn in a course. One is the material that I push in the class, and the other is that actually through self-learning, and we leverage that to teach the rest of the class. So my expectation is that each one of you will do a short term paper, and you will choose a certain topic. In fact, I can even float a list of suggested topics, but I really look forward to innovation from you, creativity from you, You can form groups of 3 to 5 students depending on the number of students who register for this course. I don't think I would like to have more than 12 to 15 groups because that becomes too many. So we'll decide on the number of persons who form the group, and each group can pick a certain topic. The topics could be like isogeometric analysis, which is really using splines or some such innovative ways to represent surfaces, or maybe meshless methods or discontinuous Galerkin methods, or for example large eddy simulation, fluid structure interactions, high speed chemistry, and so on. So you would choose a topic, and of course these topics are very general, so I cannot expect you that you would know everything about meshless method by choosing this topic and doing a project. So first is to choose a topic and then kind of decide what is the aspect of meshless method that you would look at. Are you going to talk about the overview of what a meshless method is compared to a method which uses a mesh, or you are interested in its application to a certain problem? So there would be some specificity in the project that you choose, and that would be determined by the material that you would read for it. So I don't expect you to write programs or do research on these topics. Essentially it's more about literature survey, reading them and then presenting it to the class so that it is comprehensible to everyone. So you would choose a topic and you would choose the literature that you would read and discuss it with me, and once we agree on it, then I will give you some time. You can prepare your presentations and we can meet and look at the various presentations on these topics. So it's summarized here that you will choose a topic, make a list of papers to explore it, and the topic as well as the literature that you plan must be finalized and okayed by me by a mutually agreed deadline. This is very important, and I think it's fair that I tell you why I do this. Many a times, because this is something extra, a term paper, it is very tempting to push it to the very end and then hurry up just a little bit before the date of presentation and put things together. Okay? I want to avoid that. So by implementing this kind of scenario, I think I will end up forcing you to look at these topics well in advance and plan your presentations. As I said, there will be homeworks, and I would expect you to submit your homeworks in time. It is also easy for me to arrange for the logistics in terms of evaluating them, and I would, because they add up to the final project, so it is only fair that to be able to pass the course you have to submit all the assignments. If you submit them by the deadline, you get credit for it, but if you do not, then you don't get any credit for it and you still have to submit the assignment. So I strongly encourage you to respect the deadlines and submit the assignments. This being an elective course and it has these very diverse topics, so I strongly encourage you to discuss the concepts amongst yourselves, either privately or through the forum that this course will use, possibly on MOOCit. But I would still like that do not collaborate on the assignments. These you should do on your own, and they would in fact help you in the examinations that will be conducted. So there will be 2 examinations, a midterm exam, so that's the weightage is about 20%, and then a final exam at the end of the semester, that's about 35%, and then a lot of weightage is given to the assignments and projects. So I have not broken up this 45% into how many assignments and how many credits for the term paper. So we'll do that as we move along. But you can see there is a substantial weightage on actually doing things and not just understanding what is given in the class and spitting it out in the exam. One minor point that I will not be able to give you a make-up exam if you miss the midterm, even for bona fide reasons. So if you just skip if the midterm exam for no reason, then of course you lose all credit for it. But suppose in the unfortunate event of any one of you falling sick, then with appropriate certification, I should be able to prorate your score for the midterm from the other scores. So that's about it as far as the course policies are concerned. I hope we have a very enjoyable semester and we can discuss this in one of the discussion hours. Thank you very much.